All right. Again, welcome everyone to our seminar series. This is the third seminar series organized by the TCGCC, and this time we are joined by ETI-MLC. The topic of today's seminar is the future 6G paradigms, AI-enabled networks, cross-layering, and wireless access. So we will first start by introducing the organizing committee. I am the host or the chair of this webinar series. Actually, not the series. I mean, the series will continue throughout the year. I have been an organizer for the first one, and now this is the third one, and hopefully we will do many more seminars and webinars like this one. I am joined by Dr. Kun Wang from UCLA, Dr. Carlo Fischione from KTH, who is the chair of the ETI-MLC, Dr. Zhang, who you heard at the very beginning, who is the chair of TCGCC. I had mentioned about this program at the very beginning, but I would like to repeat it again. I think we are about 100 participants, and I was seeing that this number was ticking up at every second, and it is still continuing to go up. So it's always useful to repeat the program again. First, we will start with Dr. Muriel Medard's talk. This will be continued by Q&A, then Dr. Lajos Hanzo Q&A, and then Dr. Halim Yanikomeroglu. We will try to wrap up close to 11:30, 11:40-ish. So please stick with us and enjoy the seminars. So I am very pleased to introduce Dr. Muriel Medard. She is a very well-decorated researcher. She's an IEEE Fellow, AAAS Fellow, and NAAI Fellow. She is the Cecil H. and Ida Green Professor at MIT, USA. Her talk's topic is learning the noise instead of designing the code. I won't read her abstract, but I will read her bio. Dr. Muriel Medard is the Cecil H. and Ida Green Professor in the Electrical Engineering and Computer Science Department at MIT, where she leads the Network Coding and Reliable Communications Group in the Research Laboratory for Electronics at MIT. She obtained 3 bachelor's degrees, EECS, Mathematics and Humanities, as well as her MS and Science degree, all from MIT. She's a member of the U.S. National Academy of Engineering, elected in 2020, a fellow of the U.S. National Academy of Inventors, elected 2018, American Academy of Arts and Sciences, elected 2021, and a fellow of the Institute of the Electrical and Electronics Engineering, IEEE, elected 28. Muriel was elected president of the IEEE Information Theory Society in 2012. And served on its board of governors for 11 years. She holds an honorary doctorate from the Technical University of Munich, given in 2020. Without further ado, I would like to leave the floor to Muriel Medard, and I would like to also express my gratitude for accepting our invitation to give this webinar.
Thank you very much for the kind introduction, Mel, and thanks to the organizers, of course, Mel, Jan, Kong, and Carlo for inviting me today. Let me go ahead and share my screen. Can everybody see it?
Yes, we can.
Fantastic.
See it.
So the topic is actually going to be about what I think is a very interesting new area of application for machine learning. And it was funny because I was actually co-teaching a core machine learning class at MIT last term, which you can imagine has 500 students, and really trying to think a little bit more as to how to connect it with my main research interests, and it struck me that actually the work that I've been doing with my collaborator Ken Duffy from Maynooth University lends itself very well. So this is opening up a new set of directions, I think, in this research that intersects between machine learning and communications. It's also, I regret to say, closing one, I think. It's a sort of redirecting our efforts into a more fruitful and promising area of investigation. Okay, so let me say what I think is basically one of our core needs right now, which has been, I would say, desideratum for 5G. I think we agree it hasn't happened yet, but it has been ultra reliable, low latency communications. And the reason it hasn't really happened is because the reliability has included coding at the physical layer, transport protocols. Many of you have heard me talk about transport protocols, particularly network coding for lowering delay. I'm not going to talk about that today, but certainly the coding at the physical layer is a major impediment, and we'll see why. It's not just the length of the code, it's also the interleaving that's happening. So the reliability requirement is right now, given the techniques we're using, in contradiction with the low latency requirement. The way we've done low latency is basically, and you see this very, very vividly in 5G, we've just added spectrum. We're not really adding spectrum because we have a huge need for more data. We're adding spectrum because we're replacing good engineering by just doing things faster, okay? So rather than changing the way we're operating, we're just doing it much faster, getting done more sooner, but of course at the cost of a huge amount of spectrum. And I think this is also very important for the energy aspect of the other interest group, which is co-sponsoring this event, is actually costing a huge amount of energy to be doing things so fast. So what we've been doing is just in effect running around fast forward motion by adding spectrum. Okay, so let me talk about this coding at the physical layer. What is it that we're doing so far? So again, just for the sake of, I'm not picking on 5G, but just for the sake of illustration, let's think about 5G. So what's the typical bit flip probability right now in cellular comms? We can quibble, but it's somewhere between, say, 10 to the minus 2, 10 to the minus 4. When things are not very good. Very often, actually, it's around 10 to the minus 5, which is why, and we'll see that later, when you see people doing chip comparisons, energy comparisons, they look at typical operating regimes. And so it's almost all the typical operating regimes for chip comparisons are at 10 to the minus 5, because that's the more common regime. So you're really thinking that things are going wrong when you're around 10 to the minus 2, 10 to the minus 3, but most of the time you say around 10 to the minus 4. What should be the channel capacity? What should be the highest rate achievable? Well, it basically should be 1 for all intents and purposes, okay? It's upwards of 0.9. What are the rates that we're getting on our data channels? They're parlous. Okay, I mean, we talk about, capacity achieving codes, but who cares about capacity achieving codes? We couldn't hit capacity, if we tried throwing a rock at it. We're going, at rates around 1/2, 3/4, very far from capacity. So who cares if we're using LDPCs or other fancy codes? We're very far from capacity. To make matters worse, the codes have always been designed in terms of ID channels. Channels are anything but ID. I'll show you a picture a little later. I mean, we know it, but sometimes it helps to see a picture to really fix in our minds just how far from ID they are. So because they're not ID, we make them appear ID, we mimic them. We interleave over thousands of bits to try to make them appear ID. And that is actually introducing a huge amount of delay. So why are we doing that? Because we have been building codes. And, I mentioned that I'm trying to open a new area of investigation in machine learning communications, but I'm maybe unfortunately closing another one. And the one that I'm closing is actually going to be, frankly, the research of better codes, because we will see that pretty much all codes are good. But we should stop trying to make them, and we should stop being guided by the construction of codes. So the approach here that we're going to take is this guessing and random additive noise decoding, GRAND. Now, if any of you have spent more than about 10 minutes in Ireland, you know that they say GRAND to everything. So it's a bit of a tip of the tip of their hat to Ken's background. But the idea behind this is we're going to be focusing on the engineering needs. So we're not going to let the math, let's say traditional coding theory, dictate what we do, make us use these long codes, which are not even giving us what the math was going to tell us that we were going to get. They're not giving us capacity. We're very far from capacity, making us use our channel as though it were IID when it's not IID. We're going to focus on the current engineering needs. So remember, what is it? We want low latency. Okay, so we want to control length. We want to avoid interleaving if possible. But there are other desiderata. We'd like to have flexibility. We've all followed, the major drama that happened in 3GPP in the context of 5G about which codes to choose. Let's forget about which codes to choose. Let's have a single decoder that decodes all codes. Okay, and then people can choose whatever code they want. As we'll see, they're pretty much all good when you decode them correctly. And of course, we should be going to higher rate because when we're going to lower rate, it increases somewhat our delay. And of course, it's making us pay money for bandwidth and energy, which we're not using efficiently. Again, it's bad engineering. Okay, so we're going to make the math look like the engineering. The engineering should be the leading term here should be that which determines how the math is done, not being led by the math, which was done for other purposes. Let's just quickly review the principles of coding. What are the principles of coding? I have my data. I compress it. I do source coding. So I have a source. I compress it down to an entropy, down at best to the entropy of that source. So say that here, each of these blocks is 1,000 bits. I went from 4,000 bits to say 2,000 bits. This was my compression. Let's say gzip. I then took that data. I coded it to send it over a channel. So maybe this is a rate 2/3 code. I took 2,000 bits, I turned it into 3,000 bits. And my rate is to be lower than capacity, which is for a binary system is 1, because 1 would be the best I could send for a binary system with no errors, minus the entropy of the noise. So you see the entropy showing up here. And of course, the entropy of the noise is the entropy of this deleterious effect, which happens when I send data over a channel and some of the data is corrupted. So that corruption of the data is showing up here in my second block. Some of the bits here were affected. We generally denote this by an addition of noise. If I'm using a binary channel, for instance, a binary symmetric channel, then we can think of this as adding a noise, which is in a binary system, in effect, XORing the original bits with noise. And so if I'm talking about a bit flip probability of 10 to the -3, I'm really talking about a noise which is equal to 1 with probability 10 to the -3, and the rest of the time it's 0. It's not affecting the output. Okay, let's do, so why am I reminding you of this? We know that basically when I do compression, I'm saying that I had say 2 to the n possible strings if n was the total amount of my data, length of my data, and I narrowed it down to actually fewer possibilities. So if here I had 4,000 bits, I had 2 to the 4,000 possibilities, but actually because of sparseness in the data, I could compress it. And I went down to just 2 to the 2,000 possibilities, okay? Here, if I had now n is 2,000, I expanded the data to send it over the data, or to send the data over the channel to 3,000 bits. But out of these 3,000 bits, because it came from this original 2,000 bits, I actually only have 2 to the 2,000 possibilities. So here I have a data here of length 3,000, but I have a code rate of 2/3. So I have 2 to the 2,000 times 3,000 times 2/3. So actually 2 to the 2,000 possibilities, which came from this original 2,000. Okay, and I send it over the channel. Now, the nicest code that could ever happen to me would be the code that, obligingly compressed the nicest noise that could happen to me would be the noise that obligingly compressed itself and place itself at the end of my transmission, right? Everybody would know how to build a code for that. So if I had a channel where I know that the noise is going to appear in a compressed form at the end of my data, that would be fantastic. What would I do? I would send my data uncoded, and I would just sacrifice the last bits, the last 2 to the NHN bits to my noise, okay? That would be, of course, the best that I can do. That's what the coding theorem tells us, actually, that would be the best that we can do. And we can see why, right? I mean, I need to fit in both the data and the noise. I need to remove the noise. And so I would love it if the noise just stuck itself at the end in a compressed form. Now, how many bits do I have on my output? Well, I sent 3,000 bits. I have 2 to the 3,000 possible channel outputs. So these 2 to the 3,000 have to fit in both my strings of data, of which there are 2 to the 2,000, and my strings of the noise. If they had, again, in the most easy to manage way, stuck themselves at the end. Okay. So if I had this very considerate noise that self-compressed and stuck itself at the end, I would have 2 to the NHN strings. And this 2 to the N has to fit in both the data, of which there are 2 to the N are strings. Again, here, that is to the 2,000. And the noise, of which there are, with high probability, that I really need to worry about, that I can recover from 2 to the NHN. In the same way as there were this many strings here when I was compressing the data, there are really only that many strings of noise that I need to worry about. If I'm outside that set of strings, I get an error and there's nothing I can do about it. So that means that my output has to fit my possible input strings, 2 to the 2,000, and my possible noise strings. So in order to be able to recover the data, it needs to be that the number of possibilities in my channel output, to the N, in this case to 3,000, exceeds 2 to the NR, which is 2 to the 2,000, times 2 to the NHN, which is the number of probabilistically significant noise strings. And that's what gives me, if you look at the exponent here, that 1 has to be greater than HN plus R, or equivalently, this is what gives me Shannon's capacity, 1 minus HN. Okay, this is the easiest proof of the coding theorem you will ever see. All right, now it's clear that the best that I could do is to have the noise, as I said, very unobtrusively place itself at the end. But how do I actually get that? Because the noise is not doing that. How do I actually get to that performance? Well, Shannon's idea was the following. He said, let me pick a random code book. So what does it mean to pick a random code book? I have a bag of all 2 to the N possible strings with all 2 to the 3,000 in the example I just gave. And I have 2 to the NR, so all the 2 to the 2,000 possible messages. I pick sequentially the messages, and I pick with replacement in the bag of 2 to the 3,000, the 2 to the 3,000 bag of 3,000 length strings, and I assign to each message a string, and off I go. Message, string, and off I go with replacement. Okay. And how do I decode? So the encoding is very simple, but we'll see later that there are some complications. The decoding idea is that he's going to look at the Y, going to look at the output, and he's going to stare at the output and say, of all the 2 to the 2,000 possible strings in my code book, which one gave me the maximum a posteriori probability? Now, if all the input strings have the same probability, which we assume because this compression happened, then what we're going to have is that the maximum a posteriori is the same as the maximum likelihood. Okay, why do we not do that? 2 reasons. Reason 1, if N is, say, 1,000 bits, we saw lengths of that order with the 5G LDPC example I gave you, and R is large, right? And we'd like R rate to be large, then 2 to the NR is huge. So that idea of taking the strings with replacement and assigning them arbitrarily, randomly to the messages is not going to work, because I would have to record all those assignments, and that would be storage-wise impossible. The second difficulty is the computation of, so this first idea here is computation, is storage-wise infeasible. The second difficulty is with the maximum likelihood. How can I do that computation of looking at all the possible outputs, of all the for each output, looking at all the possible inputs and doing the maximum likelihood? That would be too difficult. Okay, as a result of this dual difficulty, we have been creating codes, block codes, convolutional codes, which are basically like block codes just over different algebra, so-called modern codes. Why so-called modern? Because, you know, LDPCs have been around since the early 60s. Rateless codes, network codes, you know, you've heard me talk about modern codes, about rateless codes, but let's say polar codes then are, you know, sort of the first well-established, if you will, a priori systematically shown to be capacity achieving. So constructed codes to be capacity achieving. And there is right now a large interest in using machine learning to build better codes. But the reason for this is this dual difficulty of remembering the code construction, and secondly, of decoding. So the first difficulty, actually, the storage, has been obviated. It's been obviated ages ago. It's been obviated in the late 60s, early 70s by Gallagher, who was my advisor. He showed that linear codes can fix this. I only need to choose a random generator matrix. So the storage difficulty is gone. I don't need to record that assignment of message to randomly picked string. I only need to take the messages expressed as strings and multiply by a single randomly chosen matrix. It may need to be a somewhat larger field, but let's leave that aside. It doesn't matter. So the random codes from Shannon actually are equivalent to the random linear codes from Gallagher. Okay, so recall now that then we only have one difficulty. You know, again, let's remember why we're doing all this coding. Why are we doing all this effort? It's not because of one anymore since the 70s. It's because of two. It's the decoding. Okay, so all of this stuff has been because of the difficulty in decoding. Why is the decoding difficult? Let me go back to this picture. We have always been looking at Y and trying to determine what X was. Okay, but I have X plus N. If instead of trying to figure out what X was, I tried to figure out what N was, 2 to the NHN, remember when my H is, HN is small, and we told you it's around 10 to the minus 2, 10 to the minus 3, this is going to be very small. Even if N is around 1,000, if HN is around 10 to the minus 1, this is order 1, okay? 2 to the NR is large because R is large. 2 to the NHN is small. So rather than look at the big thing, let's look at the small thing. This is not the same as denoising. In denoising, you try to figure out what the noise is and subtract it, then you're done. Here, if we guess incorrectly the noise effect, then I can check whether indeed what I received was the received code word. If it's not, then I say, wait a minute, that's not the right thing. What's the second most likely noise? And this will actually give me the maximum likelihood. So instead of looking at this large to the NR, which is everything that's been done so far, we're going to look at the small to the NH. Okay. And we're going to be guessing, and this is also not the same as a dual code, because a dual code is always doing the worst case with respect to the noise. Okay, just in case you're asking. So this is something that we published a couple of years ago in IT transactions. And the idea is we're going to identify the noise using the statistical structure. Okay, remember the noise is very sparse, 10 to the minus 2, 10 to the minus 3. We'll see later what happens also if the noise happens to have correlation. So the idea is the following. I'm going to guess the noise effect. We'll see why effect later. It's be important when we go to continuous models of the channel. And I'm going to guess the noise effect from most likely to least likely, subtract the noise effect from the received signal. If the resulting signal of Y minus the noise effect is indeed in the code book, that actually was my maximum likelihood. Okay. This is a universal decoder. I'm only using the code book here as a hash, as a verification. Okay, so I'm really only using it here as a verification step in my algorithm. Okay. The complexity is a function of the noise, not of the code rate. It's not going up with code rate here. It's just depending on the noise. And this is just the redundancy. The number of bits that I need to sacrifice, and which I would have to sacrifice even if the noise, remember, had been so kind as to place itself at considerately at the end of the transmission without messing with my bits. Okay. So so now let's look at these codes that we know how to put: block, convolution. I'm not going to look at long codes right now, turbo and LDPCs, because I actually don't need long codes here. Which codes do I have which are short to go back to ultra reliable, low latency, to the short codes? That is actually what we want. We have block codes, we have convolutional codes, we have polar codes, we have, of course, random codes. So what I'm going to show you is a chip which we just presented at ESS Circ this month. This was done with Ken and his group, and with Rabia Yazizgil and her group at Boston University. What we're doing here is we're showing you a single chip that can do BCH, it can do any code. BCHs, polar codes. This is actually the first hard detection decoder of polar codes. It can use CRCs, and we'll investigate CRCs a little later again. It can do CRCs as error detection codes. Why? Because remember, I'm only using the code as a hash. It can do Reed-Muller codes. It can, for the first time ever in the world, do random linear codes. All of these codes are in one chip. Okay. The world is our oyster now in terms of code construction. Rather than classic codes such as Reed-Muller and Reed-Solomon, where I only have certain code lengths, certain rates of it, and only certain code lengths available. I've plotted them here. Of course, we can do puncturing. Puncturing is a dark art. Or looking at more modern codes such as CRC-aided polar downlink codes. Again, only certain available code lengths and certain rates. I can use random linear codes, which exist at every length, any rate, it doesn't matter. And are theoretically fantastic. These are the converse bounds of from a nice repository named Spectra of bounds on shortcode performance that is curated by my colleague Yuri Polyansky at MIT. Here's capacity. Here's a converse. We cannot do any better than that. Okay, this is different code lengths. These are different rates here. These are different theoretical bounds, which up until now have never even been reached in practice. This is where random codes are. They're above the best known bounds. They're really very, very close to the converse. Up until now, this was not doable. We can do it. Here's our chip. Here's our measurement setup. This was done in 40 nanometer CMOS. And here we go. We can do existing codes such as Bose-Chaudhuri-Hockenheim, Reed-Muller codes. We can do codes that could not up until now be decoded in a hard decision. Random linear codes, CRC, polar codes, CRC-aided polar codes. What you see in dashed lines is the theory, which again, for many of these was not doable up until now, but now we can do it. And what you see in full lines is the measurement from the chip. So this is done. Okay. This is the first universal chip using GRAND, a group in Canada, Gross's group at at McGill has done a synthesis, so not an actual chip, also using grants. So we're, other groups are using our algorithm now to try to do chip development. And there's been some other publications from Huawei and others, but this is the first chip which we have done. Our average power is actually very, very good, as you can see. And what I want to also point out is we have the best in class latency in terms of microseconds per code word. So even though it's universal and code word independent, we have the best latency. Remember, we're trying to do ultra reliable low latency. This by a long shot is the best latency. Okay. Now, why did I harp on the fact that we're doing noise effects? The fact of doing noise effects is because if you have a binary symmetric channel, you can guess the error as just being a bit flip, right? There's a discrete number of errors. If I'm using a continuous system where we have, say, a soft information, then the noise now becomes a much more complex type of phenomenon. However, the noise effect is still of either flipping a bit or not, but the noise itself is more subtle. We have shown actually how to do soft grant. Okay, and this is a paper that Ken and I showed with our student Amit Solomon, who just recently graduated his PhD. We showed this at ICC. And you can also do simplifications of full soft grant with something called ORB grant, order reliability bits, which was presented at the ICAST this year by Ken. Just to give you an idea, these are the block lengths that we can do with soft information. Okay. These are the rates. So, again, it's about the redundancy. It's not about the rate. It's not about the length. It's about the total redundancy. And you can see here the log of the block error rate that we can obtain for different systems here. Okay. This is something that we just presented at ICC with our student Wei An. What do you see here? You see here is the state-of-the-art CRC-aided Polo code with a list size of 16. Okay, so this is like the Talon Vardy decoder, which was licensed by Samsung in 2018 for CRC-aided Polo codes. Okay. This is the size of 16, which is better than most chips do. Most chips do 8, so they're actually worse. This is what we do. Okay, we do much, much better. Here are Polo codes. This is with the successive cancellation, the original Polo decoder. This is our decoder. We basically are the same. Polo codes are actually not that good, is the bottom line. CRC-aided Polo codes are much better. Now, why is CRC-aided Polo codes better? Because of the CRC. If I replace all of the Polo bits with just the CRC, okay? So let's be clear here. This is the dumbest code known to mankind. This is just a CRC. This is all these codes have the same amount of redundancy. So Polar with 11 bits of CRC or 24 bits of CRC. Those are the two possibilities under the 5G NR standard. Well, this is something where I've replaced all of the bits with just CRC. All of them have the exact same performance if you decode them correctly, if you decode them with grant. Okay, so all codes are good, basically. Same here. This is with a lower level of redundancy. This is how much we outperform. As you can see, we outperform by, here we're by about, by about a dB and a half, by about 2 dB here, by about a dB and a half. The best in class, actually, this is better than the best in class chip for CA Polo codes. Okay. All codes are good except constructed codes. CRC here is excellent. Let me go back to the topic of interleaving, which is the last topic that I'm going to cover today before I take questions. I mentioned that we all know, excuse me, that channels are not IID, okay? Channels are anything but IID. This is a channel before interleaving. That's a channel after interleaving. If you looked at that channel before interleaving, you would never describe it as IID, okay? And the interleaving, for instance, if we use the standard IEEE interleavers, are thousands of bits, huge amount of redundancy. Here is BCH code. The line here in turquoise is a Berle-Massey decoder, excellent decoder. And you can see our decoders just as well, okay, with a fully decoded, fully interleaved system. The G here is indicating the memory in a Markov channel. Okay, so we assume that the channel is Markov. We don't even have soft information here. We just assume that we know that the structure of the channel is Markov. So we have some idea of the Markovicity. Okay. If I apply a Berle-Massey decoder to a channel with more and more memory, with a higher order of Markovicity in effect, it gets worse and worse. If with our system, unless the channel has so much memory that it basically exceeds the length of the code by a large amount, we actually do better with Markov ordered guided GRAND, what we call GRAND MO. Excuse me, we actually do better. This is from a paper called, quite bluntly, Ditch the Interleavers. So what do we see? We gain a power factor of about 2 or more, 3 dB. But even more importantly, because we don't need to interleave, we have a delay factor over 100. Let's go back to the beginning of our talk. How would you get a delay factor over 100 right now? You would buy 100 times more bandwidth with the attendant cost in bandwidth, tens of billions of dollars being paid in the last 5G auction, and of course corresponding energy loss. So just to reiterate, we're going to make the math look like the engineering. The idea is, let's focus on the noise. Let's not really worry about the code. Any old code is good, pretty much. Just use a CRC. It's as good as the best, it's as good as CA Polar codes. It's better than Polar codes. Let's not worry about the code. Random linear codes also do well. Everything does well except for a small set of constructed codes. Worry about the noise. Let's learn the noise. And with that, I will stop to make my 10 a.m. Stopping time and have a little bit of time for questions.
Well, thank you very much, Muriel. It was an excellent talk. Now, I would like to start the Q&A, and for the audience, you can type your questions to the chat window, or if you want to ask it, you can unmute yourselves and ask your questions. We will have approximately 5 minutes, and if you have more questions, then I will curate the questions and send an email to Muriel. But before that, actually, I want to mention one thing. Our attendance is increasing on Zoom and Bilibili platform as well. I just checked maybe 10 minutes ago. We had reached 3,000 participants on the Bilibili platform.
Okay, so I only see the people on Zoom. So hi to the other participants. Yes, wonderful.
Very good, wonderful. So let me open up the Q&A with something we have been hearing a lot in the recent days or maybe years, and I want to pick your brain on this. What are your thoughts on semantic communications and how we can apply the idea of learning the noise, the environment to these relatively new concepts of semantic communications?
That's a good question. I haven't really given thought to semantic communications, but I think maybe your question is also a little related to the one that I see that just popped in the chat. And for the people who are the attendees who are on a different platform, I don't know if you can see the question in the chat, so I'm just going to read it out, which is a question by Geeta Chandrasekaran. How does mobility impact performance of your algorithms? I think it's a little bit related to what you're asking, Mel. Okay, so I'm going to just meld the two if you don't mind. So if I have mobility, and I have some notion of mobility, whatever I know, then in effect, what I should have is, and I think, Lajos, this is an astute question, Geeta. Perhaps we could expand the question to channel statistics, as actually that's exactly what I was going to do. Is sorry, let me just jump to the right spot, and my system has frozen. So actually, this is maybe not a bad spot. Let's look at anything here that affects the number of strings that I'm going to guess over. Okay, anything here that affects the number of strings that I'm going to guess over. For the same number of errors, if my errors are more clumped, or there's any sort of statistical structure, then actually I'm more likely to guess. I can withstand more errors for the same number of guesses. Okay, so it turns out that one of the things we see, I haven't covered here, is that when we have any sort of correlation, such as would occur in with non-uniform statistics, such as would occur with mobility, going back to Geeta's question, which is they just pointed out, wondering how mobility and Markovian dependence, so the Markovian dependence would go with mobility, very much so. And for those of us who have worked in channel statistics, we often model mobility as a Markovian behavior. Then what would happen is that you could actually go far beyond the error correcting capabilities of the code. Okay, so the error correcting capabilities of the code that come from classical coding theory are based on a notion of distance. Distance is not an actual interesting parameter. Truly, it's a parameter that came implicitly out of an ID channel model, right? Basically, what happened is we gave, sorry, for whatever reason, I'm having trouble going back in my slides, but the comms people gave the coding people an ID channel model. The coding people said, okay, that's what you gave me. I'm going then to assume basically that, that distance is the important thing. And I'm going to do massively clever discrete mathematics to give you codes, to give you distance. But here, actually, it's about the noise. So we routinely correct with Markovian noise way above the maximum distance. And that's actually something that I really want to emphasize, is basically when you're looking at noise centric, the maximum distance, shows up as just, an interesting parameter, but it's not a core fundamental parameter. Okay. Did that answer your question, Lajos? Okay, Muriel, Laya has another one. Do you see any relationship between grand and syndrome decoding? I am asked this a lot. In syndrome decoding, you calculate the syndrome. When you calculate the syndrome, you have basically tried to compress the noise. Now you have destroyed the structure of the noise, and you're going to take the maximum amount of time to try to guess that noise. So you're actually you're trying to pre-process the noise in a way which has removed all of its structure, which would have been useful for decoding. Does that make sense?
Well, Muriel,
yes, thank you.
That's wonderful. Yes. Actually, you've been melting the questions in a pot. There was follow-up questions coming from Geeta, Lajos, and then we have other questions. Thank you so much. That was really great.
Yeah, Suman had a question.
Yes, there's one short question from Suman. Let's answer that one too, and then that will be the end of Q&A. So if you still have questions from the audience, please type it in. I'm going to take them and then give it to Muriel at a later time. And also please give your emails at the end of your questions so that we can put you in contact. So Suman's question. Let's do the last question. Yeah.
Yes. So the set of possible noise that were likely, is that taken at various time intervals or single time intervals? The set of possible, okay, this is the realization of the noise. If I understand your question is you're asking, am I averaging over multiple noises or not? And no, this is per realization, which is what is allowing us to go to short codes, right? So why do we go to long codes? You know, why did I say that we've been letting the math, you know, guide what the engineering was doing? The reason we're going to these, you know, ridiculously long LDPC codes is because we're going to try to average, you know, so that my sample is close to the average by doing basically concentration to the mean. I'm not doing a concentration to the mean because I'm doing per instance. Okay, so per short code word, I'm looking at the most likely noise, and I have a pretty good idea of what the most likely noises are. And actually, the shorter the code word, the faster I'm done. Okay, I'm not trying to do a concentration to the mean. I don't need the concentration to the mean. As a matter of fact, if you look at the analysis in our paper with Ken, it's not a concentration to the mean, it's a large deviation analysis. It's completely different math.
Well, thank you. Thank you so much. Thanks for the talk. Thanks for your time. It was a great pleasure having you,
Thank you for inviting me. And I'm so glad there was such an interactive crowd. I really appreciate it.
Thank you. Now I will start sharing my screen so that we can switch to our next speaker, which is a very distinguished member of our community, just like the other speakers. And I would like to invite Carlo Fischione for introducing Dr. Lajos Hanzo.
Thank you, Mel. Thank you so much. And it's now a great pleasure for me to introduce Professor Lajos Hanzo, who has a really remarkable set of achievements in his impressive CV. And I will shortly mention that he's fellow of the Royal Academy of Engineering, he's fellow of the IEEE, he's fellow of the EIT and of EURASIP also, and he's a foreign member of the Hungarian Academy of Science. He also honorary doctorates from the University of Edinburgh and the Technical University of Budapest. He has co-authored almost 20 books and almost 2,000 publications on the IEEE. And please, Professor Hanzo, the floor is yours.
Well, thank you so much, Carlo. It can only go downhill, really, from this point. You sort of embarrassed me with all the things I've done in the past 40-odd years. Anyway, it's great to be with you all, and I'm just going to share my screen. The host disabled participant screen sharing, so are you able to allow me to share? Or maybe Muriel has to unshare first, I don't know.
Oh, I just made you a co-host, Lajos, so
okay,
now you should be able to share.
Let me try again. Oh yes, it looks much better. So I wonder whether you can see my screen now. Are you able to see it? Okay, brilliant. So Muriel invited us for a lovely sort of stroll of coding theory, and it's so nice to see that you know, this was a historical perspective as well as drilling down in a very sort of topical subject, and you know, really exciting. So I'm going to look at some of her papers again. That my talk will be more like perhaps galloping a little bit rather than taking you for a stroll, a leisurely Sunday afternoon stroll. But my main objective is really to sort of inspire you rather than necessarily inform you about minute details. So I will be glossing over some things, and I will be, you know, really providing hopefully a broad picture to enter a new area of research. And so This is the longest title in the universe, probably. Imagine if I had spelled out all these acronyms, but of course in this community they are really well known, so there's no need to do that. But I will not give away the answer to this question until the end. But let me just really thank Mel again for the invitation, who is also a valued collaborator of mine, and also Zhang, and to you, Carlo, and then of course the team back at base with whom I enjoyed an enlightening sort of long ride, and the sponsors. And so I will just show you here the map where I sit. You probably, well, hopefully see my cursor. This is where London is, as you see. I'm circling there, and Southampton, little Southampton is down here. Next to the Isle of Wight, and so this slide has the title of A Journey from Marconi to 5G during the comms version 1.0 era, because this is the place where Marconi for the first time ever demonstrated the feasibility of radio transmissions across the Atlantic. And so
Professor Hanzo, excuse me.
Yes.
Oh, yes.
Yes.
Excuse me if I interrupt you. It seems that there is some noise from your microphone. And
Okay. Let me just try and see whether I can adjust the level. Is it better now? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Now it's definitely better. Yes.
Let me go down again in level. 1, 2, 3, 4, 5. Any better now?
Even better now. Yes.
Even better. Then I
Yes.
take it down further. So 1, 2, 3, 4, 5. Does it sound better now?
Now it's very clean.
Okay. So yeah, thanks for letting me know. I wondered. I should have done a test really at the beginning. Anyway, so this is just the historic preamble, warming up to a more technically minded discussion. And this is our little building at Southampton Wireless. And some of you who work in optical communications might know about the Optical Research Center, which is a famous research center with a lot of great inventions like the erbium doped fiber amplifier, for example. So, I continue my journey now for a moment with Gordon Moore. Back in 1965, he sort of predicted that every 18 months or so, the integration density will be doubled. And so hard to believe that for so many years, almost 60 years, these predictions have been valid. And so we ended up, instead of the brick here at the left-hand side with the smartphone, and 5G is being rolled out across the globe. I also have different versions of this little slide, which basically indicates how the different threads of science, including coding and MIMOs and the various transmission technologies, they result into a confluence of ideas, and eventually they merge onto 4G and then onto 5G. And although I quite like to talk about quantum communications, and I do think that Muriel's grand algorithm has actually great potential in quantum coding. So that's where I might like to try these ideas. But today I'd like to really talk about another tangential, well, actually more like a parkway rather than an avenue or a motorway even, to the 6G technologies. And 6G, we know it's kind of thundering along now. You probably know this book, which has a whole host of ideas, but of course everybody is just hypothesizing at the moment what 6G will be like, and most of us have actually our own list of maybe half a dozen to a dozen critical enabling technologies. And of course, it's only time will tell how the political wranglings in the standardization bodies will pan out in the end. So sometimes I go on a long walk with my dog, and I teach my dog AI and deep neural networks and all sorts of other things. And so the rest of it will be all about maybe how to teach my dog AI and the basics of communications. And you recall that I had these famous acronyms, the enhanced mobile broadband, and Muriel eloquently spoke about the ultra reliable low latency and how, in a degree, how macabre almost this is, because ultra reliable and low latency until GRAND was invented was more like a science fiction idea. And then, of course, we also have the massive machine type communications. And these really, really attack the communications problem from a very, very different angle. So I call this now a journey from 5G to 6G with that piercing question as to whether they will prevail in the 6G era or whether other, dominant operating modes will take over. In this slide, it becomes really kind of plausible that the propagation properties are really friendly below 2 gigahertz. In fact, some of you, the oldies on the audience might remember GSM was the first system which turned out to be a global mobile system, and initially it used 900 megahertz as its carrier frequency. But before that, the analog systems actually used 450 megahertz. And then only because we needed more spectrum, as Muriel underlined, we opted for higher and higher carrier frequencies where, of course, more bandwidth became available. But at the same time, unfortunately, the propagation properties become more hostile as and when we sort of inch upwards in the frequency range. And although 3GPP considered the millimeter wave frequencies, and it's still a study item, but in the early stages of 5G rollout, this is not really a main theme because of the small cell sizes and the potentially more expensive infrastructure, etc. So the mobile broadband would require higher bandwidth, but these are only available at 6 gigahertz and above, where we could potentially have like up to 800 megahertz bandwidth. Again, this I would view almost like a triangle. You can think about the throughput at the tip of this triangle, maybe the power at the bottom, and the integrity at the other corner of this triangle. And historically speaking, I cast my mind back, and again, Muriel alluded to Shannon's work repeatedly. And so the community spent really about 50 years until ICC 1993, well, more than 40 anyway, in terms of trying to inch closer and closer capacity. And this was achieved with the aid of turbo codes. And then people realized that actually Gallagher's LDPC codes from his PhD could already do this. So, inching closer to capacity requires longer delay, longer code words until GRAND was invented, perhaps, but of course remains to be seen whether the standardization bodies will welcome in again a new coding scheme as such. In general, we know that decoders are never specified by the standards. It's only the encoding schemes, and the decoding issues remain for the implementer's innovation to be enhanced and discovered over time. So really moving on, I want to contrast this what we just discussed to this fairly well-known spider diagram, where we have a number of conflicting design metrics. Obviously, latency and reliability is something that we discussed so far, and potentially also throughput, which is related to data speed, or potentially even the network capacity, which takes into account the interference rather than just a single link, etc. So there is many more parameters in the system, and instead of really looking at just near capacity optimization, or in fact the green radio, and in this respect, in this committee, it may even be controversial to say that energy minimization is just one of many parameters that we really ought to enhance. And our goal should be, rather than swing from bandwidth optimization to energy optimization, to actually discover the whole Pareto front of optimum solutions. And this is what I will try and sort of really underline as we go along. So I have to speed up. This was only the historic preamble, really, and the classic outline. But I already said the motivation. Now I don't know whether Halim is online already. I haven't checked, but he speaks very eloquently, along with Slimaluni, for example, about providing coverage for the remaining 4 billion. And of course, that's again an extremely valuable objective. If I look at the coverage probability or coverage maps, which I downloaded from the internet, you see here the huge, vast areas in the north of Scotland, for example. Only the roads are covered with, sausage-shaped cells, if you like. And in the highly densely populated areas, London, Manchester, etc., you have a very good 4G plus coverage and, 5G being rolled out. But similar situation is valid in the US. The British Isles could fit into this whole white area here, probably. And again, there's no coverage there. And we know about very famous cases when planes disappeared, the Malaysian Airlines, and people disappeared, like Margaret Thatcher's son in the Paris-Dakar car race, and so on. So, obviously, having coverage everywhere is a very valuable objective, because it could also result into wealth creation. And that would help the third world as such. So India has a similar situation, and China as well, and obviously I mentioned the desert, Saudi Arabia, again, very good 4G plus 5G coverage in the densely populated areas, but you can get lost in the desert or in the mountains of the Rocky Mountains, for example, if you don't have coverage. So I try to really, from now on, focus a little bit more on, what 6G might be and how we might be able to provide coverage in the future in order to really support wealth creation and the remaining people with wireless internet, for example. So tons of papers hypothesizing, as I mentioned, and I also pulled up the 6G book. And one of the solutions that repeatedly appears on the horizon is basically the so-called SAGIN concept, the Space Air Ground Integrated Networking concept. And in this scenario, obviously, we view the system as a multi-layer structure. We have the terrestrial layer, but I would include here, for example, the ships. After all, the shipping industry is crucial for the global economy. And then a cruise ship might have like 6,000 passengers on board who only have access to meagerly low rates through the satellites. But additionally, recently there's been a lot of research on UAVs, and also there's now emerging research on aeronautical ad hoc networks, for example, complemented by the geostationary, the medium Earth orbit, and the low Earth orbit satellites. So this is what I will focus on a little more. And just really abstraction is the name of the game in this respect, where we could have the terrestrial layer again, the green dots, the aircraft, and the satellites. And then I will bring in the ships later on as well, so that we have a really closely knit global network. Now, I won't have time to take you through this complex table, but if it's of any interest to you, visit our website where you would find lots of related literature. And as we go higher and higher up in the air in a three-dimensional sort of 6G style network, already fairly mature area is that of the balloons and that even tethered balloons at low altitudes, and then airships or solar charged aircraft at 22,000 meters, for example, up there. And then, of course, these are the fixed wing glider aircraft and the civil aviation aircraft. They all have very, very heterogeneous propagation conditions. And I will just show you one set of those later on. Again, you can sort of look these up in a classic paper by Eric Haas, for example, from the German NASA. But to entertain you, these are some of the high altitude platform alternatives. You see here that it's almost science fiction, but this particularly lovely plane can stay up for 6 months. Only solar charging is possible above the clouds, and you see that the whole wings are covered by solar cells, and they only come down for maintenance every sort of 6 months. So this is the last one in the series, as I said, just as sort of entertainment. And let me now focus a little more on mobility models, and then I will continue talking about networking aspects and how we can optimize or how we can find the full Pareto front for these Sargent type systems. So these were downloaded from FlightAware, and if obviously you're connected to the internet, if you like, you can actually grab this URL, and you would see the planes, landing at Heathrow Airport, for example, circling. This is the European picture in the middle, and at the right-hand side, the North Atlantic scenario. See that they're heading westwards further north, and then coming back with the jet stream between JFK and London's Heathrow Airport, for example. And we collected tons and tons of data, which was funded by a company, and we fitted models to the mobility of the planes so that we can then start studying the networking aspects. And this is just a global snapshot. Obviously, there are lots of assumptions in what I'm saying, but I will gradually narrow down the assumptions. And you see that obviously the planes cover large parts of the world. And if I contrast this to the ships, they cover yet another large part of the globe. So you can actually see that they kind of complement each other, but I will bring them together in a single picture later on. I probably won't have the time now to talk about the different types of ships. The color coding is for cargo, cruise ships, tankers, fishing boats, etc. And so you could actually view all of these as network nodes in a sort of futuristic 6G style Sargent system, space air ground integrated network. You might argue immediately, well, there's only so many planes in the air, and that's obviously true. And so I'm not really advocating this as the standalone solution, but it can play a role in bridging, for example, even satellite nodes, and certainly help the ships very much in terms of really reaching the terrestrial network, not necessarily through the satellites, but actually more directly in an ad hoc network using the planes, for example. And the Pareto optimality comes into play immediately because we know that the geostationary satellites are at 36,000 meters. So their delay is about 120 milliseconds. That's inadequate for flawless multimedia communications. So what we see in this slide is at the left-hand side, we see the number of aircraft versus UTC time, which is now we are in British summertime. And so you see that the westbound flights are more, between 10 a.m. and increasing, and then again peters out around about 8 p.m. in the evening. But the eastbound flights kind of fill in the gaps. So actually there are planes all the time in the air, and you see that we have, for example, here the green line indicates that the minimum is at around 160 planes in the North Atlantic region. So move on and talk a little bit about the scenarios, but again, I'm just sort of touching upon the associated different mobility modes of the aircraft, because you could argue that even satellite communications and terrestrial communications operate already at technology readiness level 10 as we speak, but the aeronautical ad hoc networks are at TRL maybe 1, 2, max 3 perhaps. So this is the layer which obviously will be intermittent, but it does help to complete the Pareto optimal picture. And so down here we see the taxiing, the taking off, en route, holding, landing, and so on. And the speed is from say 15 meters per second or 30 miles per an hour roughly, and then take off, up to 150, 10 times the speed. En route, if you consider potentially even creating a link between planes traveling in opposite directions, then the Doppler frequency would be extremely high. And, this raises very interesting questions as to whether to use actually non-coherent detection, where you don't have to estimate the channel, because channel estimation would be so expensive. I don't want to digress too much into the physical layer issues now, but want to just highlight, sort of really ping these issues as we go along. So specifications and challenges, I keep banging on about this issue of Pareto optimization, and this is just a different way of portraying the same thing again. And, I now would like to just really formulate a multi-component objective function, which has in it the bit error ratio and the throughput and the power, the delay, the complexity, etc. And it's so obvious to all of us that you can always increase the throughput if we increase the power, but that degrades the power efficiency, which is not within the remit of this committee. This committee wants to improve the power efficiency. I can also reduce the bit error ratio by increasing the power, etc. So it's not just a trade-off that we want. We want to get back to that spider diagram I kicked off with. Trouble is, frequencies spectrum is, again, Muriel pointed it out, very expensive, and it's quite difficult really to find sufficiently large chunks of spectrum for the different links in this. So I will not sort of elaborate on this too much, but we described the standard systems and all the associated trends in this paper at the bottom. So, really now move on to the last substantial section, and this is where I want to elaborate on many open questions. Imagine, if we could have Claude Shannon in the committee, and he did attend conferences, of course, but probably there's nobody online who ever met him in person. But you could always turn to the great theoreticians of the early heroic era and find solutions. So I just listed here a number of questions, but this is just a tiny subset of the whole plethora of open questions. So I will get through these fairly quickly, just to really show you the channel characteristics, because the speeds are so different. So that's en route, very high Doppler frequency. Here on the vertical axis, we have the envelope or the received signal strength, if you like. And then the two horizontal axes is the time here, as well as the frequency. And so very rapid fading. It would require an excessive pilot overhead, so non-coherent detection and switching between coherent and non-coherent might be a good idea, where you avoid sending tons more pilots than data. This is the arrival scenario, much slower Doppler, much slower vehicular speed, and so the channel can be estimated now. This is taxiing, even lower speed, and this is when parking, almost at low pace walking speed. So very, very different propagation conditions. And if I look at the physical layer, we could, for example, use just a good old adaptive OFDM. Again, down at the bottom, at the left-hand side, you see the subcarrier index as the vertical axis, and the horizontal axis is the time or transmission frame index. So pretty much the same as this diagram, but looking at it from the top, basically. And so you see here that 16 QAM is used, for example, when you've got good channel quality, and in fact disabling transmissions when it would only result in the splurge of transmission errors. And so adaptivity is extremely important in this context. But of course, you could work on the physical layer using OTFS, for example, because that is reputed to be extremely good for high Doppler scenarios. And so, that's being considered by many researchers. So this is an adaptive MIMO OFDM system's capacity. At the left-hand side, the capacity versus the distance. And the reason this is plotted in this way is because really it's not easy. Without using satellites, you cannot really readily transmit over the radio horizon. And so depending on the altitude of the plane, which is typically about 10 kilometers or 10,000 meters, so as you get farther and farther, at 500 kilometers, you only have, even with the near capacity coding, 1 bit per symbol throughput. So just to delve into the networking issues now in a bit more detail. So some of you might work on this, and obviously I don't have any idea of the expertise of my colleagues online, so forgive me if it's condescending to talk about some very simple things, but very clear that if we have a source like Heathrow Airport and the destination like JF Kennedy Airport, then I could have obviously a lower transmit power to overbridge a shorter distance, but then I would end up with more hops. And so this way, potentially the delay is increased, the power is reduced, or the throughput is increased, but the delay becomes an issue. And down here in the other route, we see that longer distance requires a larger transmit power, or in fact, I just argued that for a shorter distance, the throughput is higher. And so this really shows all the associated trade-offs at a glance. And so I will now report on about a sort of set of practical experiments that we conducted. And as I said, we collected an awful lot of aircraft data, their positions and speed and various other things. This example is now for our colleagues in Australia, but we've got the European and the transatlantic scenario as well. And this really lists at the top the number of flights on the busiest day, which was June 29th in 2018, and the quietest day, which was Christmas Day. So this is the distribution. You would see here again, the number of flights in air, and down here the time. We've seen this before. I showed you this when we looked at, I think you would recall this illustration. So it's pretty much the same, but the previous one was for the North Atlantic scenario, and this is for the Australian scenario. And what we did, we fitted distributions to the real data, And we found that either normal or variable distribution could be used. And although the distribution would not be accepted at a high confidence level, but in terms of practical networking performance, there was no difference. So I'm not really claiming any novelty in this distribution fitting process, but this is the number of real flights up at the top, both on the busiest and the least busy days. And then we have here in the middle the normal distribution and the variable distribution. And so again, as I said, we documented in this paper down here that the performance, the network performance was literally identical when using the real data and the variable or the normal distribution. So putting it all together before I really conclude, we have here now everything in this picture. We have here the satellites, and the satellites are the triangles. So there's one here above Newfoundland, for example. We have done one here, and then we have the aeroplanes, which are the circles. And we just, in this picture, we show a link between a ship, for example, near New York or something like that, and my home airport, Southampton, where the Titanic sailed from in her maiden journey. And then in the middle, there is here another triangle, sorry, not another, a triangle, which is a satellite. So you see that this blue line indicates the minimum delay path, which would be really through just one hop because there's no queuing delay in the system. Then we have here, if you look at the dashed dotted line here, in the top left-hand corner, that's the maximum lifetime path. Now, why is that important? Well, we want to minimize the number of handovers. And so in that respect, it's good to have stability in the system. This is true also for terrestrial systems. And you see here the little planes, and so they all move in the same direction. And so at a similar speed. So there's like 1, 2, 3, 4, 5, 6, something like 7 hops instead of just 2 hops when we use the satellite as well. And then finally, we have the ships which have also area connections. So this is really to formulate a 3-component objective function. We didn't use here the bit error ratio, for example. This work was done by Dr. Dong Liu in my team in Southampton, who is now an associate professor at Beihang University in Beijing. So to show you some tangible data before I conclude, here at the left-hand side, we see the path lifetime versus the delay. So first, simply a 2-component objective function. And I will not be able to sort of really elaborate too much on the specific choice of the deep learning algorithm, but you would find it in this paper, which appeared just a few months ago. And then we move on to the 3-component objective function. So for example, at the bottom left corner, you can see, by the way, this is for a flight which took off from Istanbul. Melike, hopefully it puts a smile on your face, and it's heading to London Heathrow, the BA 289 flight. And you can get like 60 millisecond delay, which is really the lowest. And the path lifetime is between like 10 or maybe 18 minutes. And then you would have to hand over, and then there might be a chance that the route breaks. The other extreme here at the top right corner, you see here that the delay is about 80 millisecond because there is potentially more hops, but the path is very stable for 45 minutes, probably between planes that are heading westwards, like little ants following each other almost. And finally, this is the 3-dimensional objective function. So it's got the full Pareto front, all Pareto optimal solutions where none of the three parameters here, like the throughput, the delay, and the path lifetime, can be improved, for example, from this point where you see my cursor, without actually degrading one or several of the other parameters. And so really just trying to conclude on a bold, explicit note, I haven't even touched upon a lot of issues, even in networking, let alone the physical layer, etc. You remember my slide when I was chatting to Dr. Shannon about what to do, how to proceed. And so we need really this whole community to solve the outstanding problems. I return to the spider diagram because, again, unfortunately, my answer to the question that, just going for the free modes of 5G is not sustainable for the future. We need Pareto optimization, and we have to develop the tools as well as the enabling technologies. So the road to 6G has led to comms version 2.0. And my hope is that I was able to entertain you, and look forward to any questions by email. I know that I used up most of the time that I had available. So if Melike deems that we should just take discussions to the email, that's also fine with me. Thank you so much.
Thank you so much, Dr. Hanzo. Thank you. It was wonderful talk and inspiring. And in particular, I think that it's really exciting to think that, as you say, we are with these technologies at TRL 2, 3. It will take quite a long time before we will arrive at TRL 10. So that's good news also for researchers.
Indeed.
And I have one question. In case attendants would like to pose questions, please write them on the chat, and I will present them to Dr. Hanzo. Meanwhile, I wanted to hear just a reflection or a comment on the role of machine learning and artificial intelligence. And we have seen in some of the technical results that it's actually, you mentioned about deep neural networks. Do you think that the role of machine learning will be really important, or it's just a little addition to this complex systems?
I think this is one of the areas where it's almost inevitable that we have to use learning algorithms. I wonder whether you can see this little animation I'm running right now on the screen. Are you able to see it?
No, I cannot see it.
That's funny. I haven't stopped sharing yet. Okay. So you still only see the slides?
Only the slide.
Okay, let me try and stop, get out of the slides, and then, okay. Oh, it says screen sharing is stopped. Let me try and do this again for a moment, whether I can. No, it doesn't come up. Anyway, to answer your question, this has to operate in the face of enormous uncertainty. And so, you could potentially say, right, there's like 300 planes in the air. There's a huge plethora of different satellites up there, as well as the ships and so on. And so you could think of an unbelievably complex genetic algorithm, for example, and there's the so-called multi-objective genetic algorithm, which we have used in the past, and that is capable of finding the Pareto optimal, all the Pareto optimal solutions, but only for very small networks, like, for example, 10 network nodes or so. And so in that context, this wouldn't help. However, if we use learning algorithms which only rely local knowledge, because the genetic algorithms would require global knowledge of knowing everything, where it is, what is the channel quality, how long is the queue, etc. And in some of the literature I alluded to in the slides, actually explored this with the deep neural networks. We had 3 layers, and we had, I think, 300 nodes in the first 2 layers, and then 100 nodes in the 3rd layer. And that was capable of finding, up to a few hundred Pareto optimal operating points, which is really encouraging. So my hope is that this, to a degree, answered your question.
Definitely. And one my thought on this is that some of the research directions within machine learning, distributed machine learning, federated learning, they would require less somehow coordination. Now we can see your animation, your video.
Oh, that's great. That's great. So you see, this is just a snapshot of the North Atlantic region, and you see all the network nodes. This is, as I say, from real data. And, it is so complex that no genetic algorithm could really handle this. We published some papers with medium-sized genetic algorithms, but the learning algorithm, and as you said, for example, federated learning is also a potentially interesting problem. You could look at the security aspects as well. And so I think it's a great opportunity to develop both the application and the tools together. And, delay is, of course, an issue. So you could actually view this problem by saying, all right, so I could really get from JFK Airport to Southampton Airport in a single hop through a satellite, but the delay would be potentially higher and the throughput might be lower. So it's really a tool for finding all these points, and then in an adaptive system, opting for that particular, Pareto optimal point, which is the most suitable for the application.
Thank you. You mentioned briefly about security and privacy, and in fact, there is a question by Dr. Medard on any thoughts on where privacy fits into all this?
Absolutely. So we have got just one paper on this issue where we used physical layer security in order to look at the physical layer security of aeronautical ad hoc networks. And, it works well, but there's another very important aspect in this context, namely that large ad hoc networks tend to have a diminishing per node capacity. This is also often referred to as the Gupta-Kumar law. They written both an information theory transaction paper as well as a magazine paper, which is a marketing paper on this subject. So that just highlights again the security versus perhaps integrity trade-off. That is one of the most crucial one, because I can always use a higher transmit power, but then the eavesdropper has a better chances of detecting the signal. So that's a very clear trade-off. But I just view this as 2 components in a multi-component objective function. And as the state of the art is developing, I would love to see, including more than 3 components right now. I had a tutorial paper in the communication surveys and tutorials up to 4 components, but I'm unaware of anybody using more than 4 components because the complexity becomes vast. And so just really on a final note, I know my time is pretty much up. We have also used quantum search algorithms, which allow you to observe the nodes in parallel. And so in that respect, they are very promising, but that's obviously not for 6G. It's probably for 7G or beyond, when quantum computers become sufficiently well developed. So thank you so much, and send me an email or text me if you'd like pointers. Thank you.
Thank you so much, Professor Hanzo. I see Mel has appeared, so I think this is the time to hand over to her. Please, Mel.
Thank you very much, Carlo, for chairing this session. And thank you very much, Dr. Hanzo, for this amazing talk. I actually liked your Istanbul flight example very much. I'm really happy that you had data from that flight.
You find actually more animations when you check out the papers I alluded to, because we have uploaded these demos with the paper.
Wonderful. Thank you so much. And without any further delays, let me start sharing my screen again and introduce to you our third speaker, last but not the least. So I'm very happy to welcome today our third distinguished speaker, Dr. Halim Yanikomeroglu, who actually happens to be in the same city as me in Ottawa. Our universities are almost 15 minutes drive from each other. And he's a worldwide known person in 5G and 6G communications. So we're very pleased to have Dr. Yanikomeroglu with us. Let me briefly read his bio before giving the floor to him. Dr. Halim Yanikomeroglu is a professor at Carleton University, Canada. He received his PhD from the University of Toronto in 1998. He contributed to 4G, 5G technologies and standards. His research focus in recent years has been on 6G and non-terrestrial networks, NTN. His extensive collaboration with industry resulted in about 40 granted patents. He supervised or hosted in his lab around 140 postgraduate researchers. He co-authored IEEE papers with faculty members in 80+ universities in 25 countries. He's a fellow of IEEE, Engineering Institute of Canada, and Canadian Academy of Engineering, and an IEEE Distinguished Speaker for ComSoc and VTS. He is currently chairing the IEEE WCNC Steering Committee. He is also a member of ETI-MLC Steering Committee and ComSoc Emerging Technologies Committee. He served as the general chair of 2 VTCs and technical program chair, co-chair of 3 WCNCs. He chaired ComSoc Technical Committee on Personal Communications. He received several awards for his research, teaching, and service, including IEEE ComSoc Fred W. Ellersick Prize in 2021, IEEE VTS Stuart Mayer Memorial Award 2020, and IEEE ComSoc Wireless Communications Technical Committee Recognition Award in 2018. So without further delays, I would like to leave the floor to Dr. Yanikomeroglu. I believe you have the host privileges, Dr. Yanikomeroglu, so you can start sharing your screen.
Yes, thank you very much, Mel. How is my voice, by the way?
It's perfect.
Okay, well, I am sharing my screen. And now moving to full screen, I assume you are seeing my slides in full screen mode. Mel, thank you for the generous introduction. I had a blush here. Special thanks for organizers, in addition to Mel, Kun, Carlo, Jan.
Dr. Yanikomeroglu, I just want to mention one thing. We can see our slides in full screen, but let me see if it's only my screen, but there is a little bit of cutoff at the end.
How about now? Is it better?
Yes, it was maybe just, oh, yes, it's fixed now.
All right. Okay. Yes. Thank you very much.
Sorry about the interruption. Please go ahead.
It is also a privilege to share the platform with my esteemed colleagues, Muriel and Lajos. My talk naturally follows conceptually after Lajos's presentation. Today, I will talk about wireless access architecture, which evolves at a speed in general slower than the 10-year generation cycle. In that sense, 6G is kind of close for any major access evolution. As such, I put in my title 2040. So I would like to make a little bit more forward-looking. And in line with the theme of the day, I will highlight in this novel architecture greenness and sustainability. I would like to acknowledge my research group and collaborators, some of whom are today with us, like Professor Abbas Yongaçoğlu. I will start the discussion with some very fundamentals of wireless access. It goes without saying, signal attenuation is substantial. In particular, non-line of sight path loss is huge. And in higher frequencies, this becomes even worse. Basically, blockage and shadowing are very prominent. It is almost mind-boggling that a receiver might just receive 150 dB less energy than what is transmitted. That is 1/4 of the transmitted energy. So this is especially a problem in cluttered areas like dense urban areas. Next, the demand, that is the traffic generated in space and time, is dynamic, and it is also heterogeneous and to a large extent unpredictable. The long-term statistics can be known, but instantaneously where the demand will arise, it is next to impossible to know. To make the story more complicated, over the years, as we moved from, let us say, 10 kilobits per second constant bitrate communication towards more advanced applications like augmented and immersed reality, even a few users with 100 megabits per second or gigabits per second connectivity can result in congestion in the network. Therefore, with the emerging applications, the level of dynamicity, heterogeneity, and unpredictability is also increasing. Well, to make the story even more complicated, the supply side, that is the access network, is static. You put your base stations and it determines where the capacity is in time, in space. But there are two other less emphasized aspects, and that is capacity is non-storable. For instance, if there is no one in the coverage area of this base station, which, let us say, has a rate, can support a maximum rate of 1 gigabits per second. So 9 seconds idle, at the 10th second, I can't say that, okay, now I can push 10 gigabits per second. That's not the case. So unused capacity is lost capacity. And whenever there is universal frequency reuse, there is really nothing to transfer as well. So this non-storability and non-transferability results in big problem. And that is what I call supply-demand mismatch. You can have a dense network. Let us look at the right-hand side. This might be showing spectral efficiency or the rates, but the demand at a given instant may not be where your supply is. Just a quick back of the envelope calculation. Imagine a network with 100 base stations, each can provide 1 gigabits per second. In a day, this network is supposed to support 1 petabyte of data, which is humongous, of course. But if you collect data over a 24-hour period, you might notice that the network might experience congestion many times during the day, parts of the network, yet the total traffic might be only a few % of this 1 petabyte ultimate potential, because you would be able to handle this much traffic only if the traffic is uniform in time every second. And at any given second, that traffic is uniform at a macro level, in the sense that 100 of that instantaneous traffic appears in the coverage region of any particular base station, And not only that, that traffic within a base station is just appearing right below the base station, which would allow using the highest spectral efficiency, none of which will happen naturally. So what is our legacy solution to this supply-demand mismatch? The unfortunate answer is we designed the network for worst case, meaning that we just over-engineer, over-provision, so that any user statistically, most of the time, say 95% of the time, is sufficiently close to an access point. But in space and time, a good chunk of that provision just stays idle. And a base station, even if it doesn't have any load, it consumes a lot of energy due to cooling and electronics. So this over-provisioning results in high CapEx and OpEx, and the end result is high user fees. And once again, in line with today's discussion, very high carbon footprint. The carbon footprint of the telecom sector and ICT in general is increasing more and more. So the most fundamental question I can really think of in wireless is, what are the efficient ways of distributing and collecting radio signals? Given this supply-demand potential mismatch, can we design an access network which is more agile? Well, let us have a look at the history of radio access network. Of course, from the GSM days, we came a long time, lots and lots of enhancement over the last at least 3 decades have been introduced, from head nets to distributed antenna systems to cell switch off. And in my career, I believe I worked in all of these techniques because my primary research has been the access network design. However, the more I thought on this issue over time, I become more and more convinced that we have a moving target. So yes, RAN is becoming more agile, but then the demand is becoming more unpredictable, more inhomogeneous, and it is never sufficient. And just I will open a parenthesis here. One element that introduces great agility is ultramassive MIMO. It is a big enabler for 6G. So if I have a very large array, I can have very narrow beams with that structure. But as soon as you bring ultramassive MIMO in a city clutter, due to blockage, coverage is just limited to the immediate vicinity. So most advantage is lost when we are talking about urban areas. When I was thinking on this issue in the last decade, actually, I gave many talks with titles like Handling the Space-Time Traffic Heterogeneity. First time in my tutorial back in 2010-15 ICC in London, UK, many of you probably were there. In addition to legacy techniques like, again, cell switch off or massive MIMO or relaying, I first time advanced the idea of drone-based communications. And in particular, not in rural and remote or emergency scenarios, no, in a dense urban environment. It is not an alternative to the terrestrial network. Rather, it is an add-on to bring agility without over-provisioning. So imagine an urban area, rather than covering this area, let us say with 100 base stations, perhaps we can provide same level of service with only 60 terrestrial base stations, helped by 10 UAV base stations. Obviously, they can just go where the demand is. My group's first paper came out in ICC 2016, and we had a bunch of work in those rather early years, let us say, which is not too far away anyway. For instance, this paper by Mohammed Al-Zanat appeared in the August 2017 issue of Wireless Communication Letters. Since it is publication in the last 51 consecutive months, it was one of the most, I guess, downloaded or viewed paper in Explore under WCR. I wasn't aware at the time, that is 2010-15, but there were a few other groups working at the same time on similar ideas. I became aware later. One of them is in Singapore, Zhang's group, and also Mohammed Mozaffari was wrapping up his PhD under Walid Saad, Mehdi Benis, and Marwan Dabbas, I guess, supervision. They also have early work. I guess David Gaspard is here. He also has early work in this area. I am actually pleasantly surprised that much sooner than I anticipated, 3GPP embraced the concept as a flying base station, UXMB, in release 17. And this is back in January 2020, almost 2 years ago. Having said this, after these exciting comments, especially in urban areas, there are some practical issues with drone movement, especially within the city clutter. They also have battery issues. I think drone base stations might be very useful in especially coverage extension in suburban areas or in very unpredictable traffic situations. But I continued my thinking, can we do more? Can we have even a better design? And that brings me to the next section in the talk. And this next slide is an important slide. Let us make a thought experiment. Lajos stole some of my talk with his elegant presentation. So this might look a little bit similar, but I will try to provide a revised perspective. So way up, let us say that we put a macro base station, actually a macro base station with the capabilities of maybe tens of terrestrial macro base stations. Therefore, I call it a super macro base station. And then let us assume that it has thousands of spot beams. And with reuse, it has an immense centralized capacity. And these beams are turned on and off, and their footprint becomes bigger and smaller based on demand. They provide access wherever necessary, whenever necessary, without over-provisioning the need, which means that I can now design a terrestrial network much leaner, rather than 95th percentile, maybe for only 60th percentile, and the rest is handled by this super macro base station. Well, it turns out that this concept has quite a bit of history, at least a quarter century history in ITU. ITU defines this, it has a name called HAPS, that is High Altitude Platform Station, as a stationary object or platform at altitude 20 kilometers at a fixed point relative to the Earth. So in some sense, it is giving the impression of a very, very low satellite. And just for comparison, even the low Earth orbit satellites are in the order of 400 kilometers. HAPS is at 20 kilometers, and it is non-orbiting, unlike satellites. HAPS might come in different types of aircraft shapes. It can be a balloon. These are the earlier models. More contemporary ones are either in the form of an airship like a Zeppelin or a fixed wing aircraft. ITU's interest in the area has been actually a double-edged sword. ITU historically and until now envisions HAPS as a solution for rural and remote coverage, which is very limiting. In my talk and in my advocacy, I am advocating HAPS not necessarily only for rural and remote, but in particular urban areas, super smart cities and mega cities of the future. After all, this rural and remote coverage, there is a new enabler, and those are LEOs, obviously, SpaceX. And also HAPS, the spectrum dedicated to HAPS by ITU has been, until recently, dedicated spectrum other than cellular IMT spectrum, meaning that it would necessitate a separate device like a satellite terminal today, and no one wants to carry a separate terminal. So indeed, in my view, I'm being a little bit harsh here, but ITU's limited vision actually impeded the developments in the HAPS area. But the good news is that is changing fast. I don't want to get too much details, but first time in World Radio Conference 2023, ITU will dedicate harmonized spectrum for HAPS applications in the IMT bands, so that HAPS will be part of the cellular network potentially. So in my thinking, this is an integrated terrestrial and HAPS suite of base stations. We already have small base stations, macro base stations. Now we are talking about super macro base stations. And in this 2010-19 paper, I use the term vertical headnet. It is a headnet, but it is vertical. And this term is becoming more and more common in the literature now. And I would like to emphasize that it is not a different network. This HAPS base station is native. So on top of a city like London or Toronto or Istanbul, you might have a HAPS super macro base station or a cluster of them connected to each other through free space optical links, and they provide 3D coverage for whether they are aerial traffic, cargo drones, and intelligent transportation systems on the ground, backhauling, small cells, hotspots, you name it. And let us go back to that concept diagram here and do a back of the envelope capacity calculation. The line of sight results in the possibility of using millimeter wave, even D-band, perhaps even G-band, that is the sub-terahertz frequencies. So if I have access to 10 gigahertz of spectrum, and at 4 bits per second per hertz, if I have 1,000 beams with 250 reuse, I'm already talking about 10 terabits per second capacity. And wait, if I can have 10,000 beams, that capacity might increase to, once again, a mind-boggling level of 100 terabits per second, pretty much green. It uses batteries, perhaps hydrogen fuel, and it eliminates the need for over-provisioning on the ground, which is the need to put small cell everywhere, knowing that most of the time, most of them will be underutilized. So this might be the footprint of those different beams. As the demand moves, beams also move and they become smaller or bigger. And what is the alternative? Well, look at the beam here. This is a hotspot moving. If I were to give service with a terrestrial network, everywhere in the vicinity here, I should have had small cells because this load is moving and I need small cells in every new location. If I have HAPS, there is no need for that. And with a 0.2 degree beam width, that is the norm in next generation satellites. At 20 kilometer altitude or from 20 kilometer altitude, I can have 7-meter diameter hotspots on the ground. Now, let me open a parenthesis. Here, you might be saying, hey, where is that humongous number of beams idea coming from? Well, that has become the norm in the last decade in the context of high throughput satellites, when the network moved from broadcast to broadband mode, 10 years ago, it was feasible to have about 100 beams, but the state of the art here is, for instance, Viasat-3, which will be launched in a year or two. There might be 1,000 beams resulting in terabits per second per satellite. And the high throughput satellites actually, which that concept started with GEOs. These are all GEO satellites at 6,500 kilometers. Now that is the main enabler in LEO satellites. For instance, Telesat's Lightspeed, which will be operational in the next few years, it has 675 beams per satellite. Its capacity per satellite is low because LEOs are small, much smaller in comparison to GEOs. Therefore, they don't house large antennas. So my kind of thinking is that if today, almost today, 1 terabits per second with 1,000 beams is possible at 36,000 kilometers, in 2030s, at 20 kilometers, that is HAPS, we might achieve 100 terabits per second with maybe 10,000 beams. And I would like to emphasize that HAPS is huge. It is much bigger than LEOs, therefore, or it can be, which means that they can house big antennas. Once again, HAPS has a big history, 60 years, unbelievable. I won't get into that too much due to time. The concept became very popular with Loon, but again, this is a double-edged sword. Today, when you talk about HAPS, people remember Loon project of the last decade, which is really nothing much more than an LTE payload in a balloon. I am not talking about this. Much more advanced aircraft, incredibly, incomparably advanced payload, and it is not for rural and remote. It is for Istanbul, it is for London, it is for Toronto. Now, I mentioned briefly, big things are happening in ITU. ITU decisions will enable HAPS to become part of the cellular mobile ecosystem. I expect that later in this decade, we will see deployments. They will nevertheless start perhaps in rural and remote, but the story will become interesting later on. There are a number of interesting projects going on. They all target mid this decade for deployment. And these projects include operators. Now operators are showing big interest, like Japanese SoftBank. And I can say a few words about this Deutsche Telekom initiative. Arguably is the most advanced HAPS initiative today. Their payload is composed of almost 1,000 individual steerable beam antennas, providing capacity in excess of 100 gigabits per second, and their fixed-wing aircraft uses hydrogen power, zero carbon dioxide emission. So with that experience, in particular in the second half of this decade, I anticipate that in 2030s towards 2040s, that is the 6G on the ground, and we should be talking about 7G, if I'm not sure if this type of naming will continue, but it is not too unreasonable to expect on top of mega cities, these international space station sized big aircrafts providing connectivity and many other things. That is the next bullet. So my first playing with HAPS with my colleagues Mohammed Selim Aluni and Zishan Shakir started a number of years ago for backhauling of outdoor small cells in a hybrid FSO RF mode. And again, this might be the very first paper or one of the very first in the literature articulating HAPS use cases for urban areas. But let me move on because we have much more new work. Just in the September issue of Communications Magazine and also Vehicular Technology Magazine, we have papers on HAPS-enabled aerial highways concept. HAPS is extremely suitable to provide coverage for UAVs, autonomous and connected UAVs, for instance, cargo drones, if they are carrying goods from one end of a mega city to another end, 20 kilometers, say, the control plane is at HAPS, no need for a handoff. Giving coverage through the terrestrial network will be a nightmare in many ways. Very interesting. You can dig into this if you are interested as well. Back in 1960, and just to put context here, 1957 is Sputnik, the very first satellite, as you know. So soon after that, NASA put up a constellation of, I think we can call HAPS nodes, which were truly passive, as reflectors to improve coverage on the ground. But we, in the last 60 years, pure dumb repeaters or reflectors even, not a repeater, we can use reconfigurable smart surfaces. The large, very large area of HAPS is extremely conducive for that. We had a concept paper earlier this year in Communications Magazine, and a careful link budget analysis came out just recently in Open Journal for Communications. Another application is in transcontinental highways, whether in Canada or in Australia, where most of the population resides around these highways. You can have a long linear chain of HAPS and provide coverage. Something interesting, I am now seeing that I have only about 5 minutes perhaps left. HAPS is an ideal platform for edge computing as well. So today we have cloud computing at the core. We have edge computing at macro and fog computing at small base station. What I am proposing is in between core and macro, we have HAPS, which is super macro base station, and we might have yet another tier of computational offloading, in particular applications like intelligent transportation systems, because as these vehicles move fast, offloading to the edge or roadside unit, for instance, might result in too many handoffs. Therefore, we proposed a HAPS-based edge computing, at least some of the data which is correlated in space and time, for instance, navigation type of information, which is relevant for a bigger area, they can be offloaded to the HAPS. We have some work under review in this area and under preparation as well. Another interesting use case on the computing side is, imagine concepts, emerging concepts like federated learning or digital twin. Say I would like to have a digital twin of a downtown area. Now each base station sees only a small section of the downtown. This data has to be aggregated somewhere in the network, which is causing a lot of traffic back and forth. These type of applications are very suitable for HAPS, which sees with its bird's eye view in a line of sight manner the entire city core. Yet another application which is now very hot in emerging 6G discussions, for the first time in 5G, localization has been introduced by 3GPP. And as you know, you need 4 anchor signals for precise localization. But this data shows that in the downtown setting, due to the blockages we have mentioned, if you look at this histogram, most of the time you have one or at most two anchor, you are seeing two base stations. You don't have the sufficient 4 base stations to do localization. How about I put 2 hubs on top of that city, at one end, the other in the other end. So these are super anchors for most of the outdoor nodes. And if you can get 2 more terrestrial anchors, you are ready to go for localization, navigation, positioning. And this concept in the next decade will become increasingly important when UAVs fly within the city clutter. There was quite a mention of AI, ML in earlier talks, naturally, in this very sophisticated network architecture, which is actually composed of several networks in cascade. You are moving from terrestrial network to HAPS network, perhaps to satellite network. And then if you want to do end-to-end NFV slicing and so on, it is, and keep in mind that these networks are owned and operated by different entities, even ecosystems. So this concept in our recent work, which just came out in Wireless Communications magazine, we called it self-evolving network, and AI and ML are the key enablers in the control and management. This brings me to my concluding remarks. Now, let me compare HAPS with other types of nodes. In many ways, access nodes I meant. HAPS is like a geo because it is at a fixed location, but it is much, much closer. Round trip delay is just a bit over 100 microsecond, more than 1,000 times less in comparison to geo. Latency, sorry, the path loss is also much less. Both latency and path loss are still much lower than those for LEO, but HAPS does not orbit, and also it is big size, results in big antennas and many other opportunities. Well, it looks like macro in many ways, but it is one-shot view of a large area creates many opportunities. And by the way, since it is free space path loss most of the time, the path loss to a HAPS is, believe it or not, comparable to a macro base station, and actually to even a small cell, if for small cell, path loss exponent is 4. So it is really interesting to observe that most things we can do with GEOs and LEOs can be achieved by HAPS networks as well, and even better. And most things that macros can do also be achieved by HAPS networks, even better. And certain things neither GEOs, LEOs, or terrestrial network can do can be achieved by HAPS networks. I am not saying, by the way, HAPS as an alternative to satellite networks. I am a big believer and have a big project with my colleague, Professor Güneş Karabulut-Kurt. But here, when we talk about urban areas, HAPS networks is a great solution. As Lajos mentioned, this is even part of a bigger ecosystem, aerial or terrestrial, aerial, satellite, and also deep space networks when we move towards Moon and Mars. A very interesting pointer just happened this week. As many of you know, ITU is it's very active these days. It is defining 6G. The circular letter will be released in 2023. There is this very important document called Technology Trends, and I'm trying to contribute to that through WWRF. WWRF endorsed this statement, and let me read that. With its bird's eye and almost line of sight view of an entire metropolitan area, a HAPS is more than a base station in the air. It is a new architecture paradigm with access, transport, and core network functionalities for integrated connectivity, computing, sensing, positioning, and navigation towards enabling a variety of use cases in an agile and green manner for smart and sustainable societies of the future. So there is a possibility that this will be part of the document, and we will hear more about HAPS in the coming years. So when I look at this smart societies paradigm, the three enablers, IoT and sensors everywhere, AI and quantum are the machinery, and for connectivity, sensing and everything, it is the HAPS network. So my last slide, basically, if you look for 2040s, on top of a big urban area, we might have a cluster of HAPS network interconnected with laser links, and they are connected to other HAPS clusters and the satellite network. This creates a huge number of beams for a variety of reasons. And I would like to leave you with 3 points. We are not talking about connectivity only. It is an integrated communications, computing, sensing, navigation solution. And we are not talking about access only. It is entire infrastructure, because what you see here has access, transport, and core network functionalities. It is an evolution of the architecture. It is a vertical headnet, but the impact is revolutionary. With that, I finish, Mel. This year, we had quite a number of magazine and vision papers in this concept. This, for instance, communication surveys and tutorials paper is more than 50 pages, very comprehensive look at the potential of HAPS system. And I'm looking forward to working with you all to advance this area further. Many thanks.
Well, thank you very much for this excellent talk. It was very informative, and we have some shower of questions coming down the chat screen. So I would like to start with the first question that we received, and actually it's like the attendee was reading my mind when I was looking at your presentation. I was thinking one of my surprises when I attended a first meeting or a summit with the telecom operators was that they were discussing how costly it was to lease a tower, the placements of the base stations within the city, those kind of concepts. And at academic conferences, we discuss about very futuristic ideas, and then it comes to the operator summit, and the ownerships and the prices leasing becomes an issue. So the question comes from Fauzi, and they are asking, have you thought who is going to operate these hubs? If they are used to avoid over-provisioning of cellular networks on the ground, which kind of cooperation models could be used between the hubs owners, operators, and MNOs?
Yes, very good question and very relevant to this discussion, obviously. The reason why HAPS networks have not found much deployment opportunity so far, as I mentioned previously, because the ITU limited itself due to historic reasons, rural and remote, but there is not much business case there. And today we have satellites as a solution. And secondly, the spectrum dedicated HAPS very generously, in the order of hundreds of megahertz of spectrum, different than IMT spectrum, that is the 2G, 3G, 4G business. As I said, this is changing. It is already, just let me elaborate a little bit. Something big happened in 2019 in this area. That is the last World Radio Communications Conference at Sharm el-Sheikh, December 2019. The agenda item for 2023 was set, and one of them was a new definition for HAPS called HIPS. It is a bit awkward, but HAPS as an IMT base station. So what I call today as HAPS super macro base station, they call it HIPS, but this is not very common in the literature, so I'm a bit shy of using that. And they are saying that they can be used in below 2.7 gigahertz. So anyhow, after this, a number of operators became interested. So HAPS has a history of 25 years in ITU, but it was always championed by not telecom industry, by aerospace. So you see huge, satellite companies of that sort. One reason why Loon ended is that in their statement, news release, they said that we couldn't succeed in finding an operator to support big deployments. But now two major operators, Japanese SoftBank and Deutsche Telekom, put big money on the table, big money. They started companies to develop HAPS themselves with some, of course, help from aerospace industry. And now if you go to 3GPP meetings, Chinese operators are also showing big interest. And just a few weeks ago, or maybe a few months ago, GSMA, the bodies for operators, they are issuing white paper after white paper on the HAPS potential. So going back, it is very important to conceive this in such a way that HAPS is not a different network. It is native to the terrestrial network. So therefore, this emphasis on vertical headnet. Operators might have their own subsidiaries for HAPS operations, or there might be special MVNOs, as you mentioned, like in Canada, there might be a HAPS operator concurrently giving service to 3 major Canadian operators. If we have one on top of Ottawa, that HAPS owned by a new operator might give service or help the legacy operators, Bell Mobility and TELUS and Rogers. So this is the model I'm thinking of. I hope I touched upon the important points.
Wonderful, thank you very much. Our next question is about, actually I'm going to combine 2 questions because they are sort of related. So we have one question about uplink power requirements. So basically, are there any challenges for our devices to access these HAPS platforms? And the other question is about the interference that would be introduced by these new platforms to the existing infrastructure.
It is always humbling to talk in front of informed people, very appropriate and right questions. First of all, here HAPS reaches the smartphone or wearables, you name it. That is extremely important. If it cannot reach, if a smartphone or whatever the device we will have in 2030s cannot communicate with HAPS, then forget it. Then how is that possible? Well, it is actually, the calculation is very simple, although there might be a challenge in achieving the numbers. The calculation is a very simple link budget calculation. Here, the big issue is antenna gains. So one difference of HAPS in comparison to LEOS is that HAPS is much closer. It has a 30 dB path loss advantage in comparison to LEOS just due to proximity. But more than that, it can have much bigger antennas, maybe a few 10 dB more, then link budget can work. As a matter of fact, those of you who are interested in the satellite domain, which is also very hot, the big shortcoming of the upcoming satellite networks like Starlink, they don't reach the smartphone. You should have an outdoor dish antenna and so on, as we all know. But there are initiatives. One of them, there is a startup, Israeli-American company coming very strong. They want to deploy geo-size LEOs. Well, some of the audience may not know, but the rule of thumb is that if you go away from Earth, the satellites become bigger. a GEO is like 10 times bigger than a LEO. So they are proposing, this company, to put GEO-sized satellite again at LEO with big antennas so that they can reach the smartphone. NASA was in the beginning, was very against this due to cluttering of the space and space junk, all of these, but it seems that they are on board now. So if LEO community is very ambitious, maybe by 2030, they want to have direct link to user equipment, this is for sure doable with HAPS. HAPS even can penetrate to indoors with lower frequencies. Interference is obviously very important. And in the pictures I had to go through very quickly, in high throughput satellites, if you look at the color code, it is like GSM days of 2G. The beams do not use the same frequency. Maybe every fourth beam use the same frequency due to interference. And I think it will be a big research topic to reduce interference further so that reuse is increased. So if we have 1,000 beams, moving reuse from 1/4 to 1/2 will double the network capacity. That goes without saying. This will certainly necessitate coordination with the terrestrial network as well. But we are really talking about a much richer version of what we have observed in HETnets. So our community, when we moved from macros to macros and small cells, this discussion we had. And we have several mechanisms, power control and intercell interference coordination, and you name it. I think the same will happen when we have a 3-tier network with HAPS. We will see a lot of literature in those topics. Certainly, interference is something we have to be careful about.
Wonderful. Thank you very much. I'll take one last question from the queue of our questions in the chat window. And then the rest of the questions, I'm going to probably record them and then get back to you. But if the attendees who ask the questions, they can enter their email, then it will be easier, I guess, for you to reach out to them. And I will send them a message for this. So the question that we are going to entertain now is, how do you see the interplay between UAVs and HAPS as enablers for on-demand coverage capacity? How can AI/ML help here?
Yes. Here, when we talk about the wireless infrastructure of the next generations, and here I'm once again not limiting myself to 6G because 6G is in many ways very close. All these technologies, whether it is satellite networks, HAPS networks, UAVs, they all complement each other. It is really not one or the other, or one as an enemy of the other. The question is which one makes most sense at a given point. For instance, if we are talking about a global coverage, that vision of connecting the unconnected, the next 3 billion people, I think a dense satellite network with tens of thousands of satellites is a very good solution. But my focus, as I said, has been on smart cities, smart societies of the future. And this is a sustainable solution rather than just blindly densifying the terrestrial network. By the way, that densification will happen for sure and has to happen. Demand is increasing, but it can only happen where the customers are. That is the downtown course. As you go around the periphery, the network can rely more to HAPS. UAVs is another potential solution in bringing agility, and UAVs might have very interesting special use cases. For instance, dedicated UAVs for first responders, that is a police vehicle. If the crime scene is a little bit outside the city core, the vehicle-mounted UAV. By the way, these are already being discussed in 3GPP Release 18. The UAV mounted at the police vehicle might be launched, and it can be acting as a relay to a near 10-kilometer away macro tower. So UAVs, I think, will be there as well. But in my view, it may not be very realistic to think that in a metro area, again, like Istanbul or London or Toronto, to have thousands of UAV base stations in the city core because of some challenges, like these UAVs may not be able to maneuver between the buildings and so on. So they have a place. HAPS has a place. HAPS is extremely agile. You can just turn on and off the beams, make them smaller, big, move a vehicle. I think the much sought after agility will come through this vertical headnet architecture. By the way, Mel, I would very much love to hear the comments and counter arguments. The audience in Bilibili and Zoom can email me. I will try to provide my views to them.
Wonderful. Thank you so much. So unfortunately, we have come to the end of our time limit. We wish we could take more questions, but I have recorded the questions and I'll follow up your emails if you are sending them to me. And now I will hand over to Kun Wang for closing the webinar.
Thanks, Mel. It's my pleasure to have the closing on behalf of our TCGCC. First of all, many thanks to the three distinguished speakers from their amazing talks covering the emerging research fields from the 6G, that is the learning, the noise, the cross-layer design, the HAPS for the green ICT, etc. So the three talks give us a close look to the topic of this webinar, the future 6G generation paradigm, the AI-enabled networks, the cross-layering, and the wireless success. So also thanks very much to Mel inviting the Carlo from the ETI-MLC to organize this webinar with our TCGCC together. We know the TCGCC aims to the green communications and computing, and the ETI, the MLC, seeks to the emerging technologies for the intelligence communications. We are looking forward to the next in-depth collaborations between our two communities. So finally, I'd like to thank everyone to attend this webinar. Let me show you some statistics for our webinar. The peak number of the participants from the two live platforms of this webinar. So for the Zoom platform, the peak number is 115. And from the Bilibili platform, the peak number is more than 3,000. That's amazing, right? So I'm sure everyone enjoys it very much. So where the webinar will stop here, and we wish you a happy in the coming days. That's it. Thanks.
Thank you very much, Kun. And maybe one more addition. I believe we will be sharing the recorded video on the TC's web pages. So if you are interested, please check the TC web pages after a week or so, and you may find the link to the webinar. Now I'm stopping the recording, and thank you, everyone.